Pues empezamos, ya no va a venir nadie más.
No se puede grabar al final, ¿no?
Sí, está grabándose, pero en el propio ordenador, no se va a grabar. Pues, bueno, buenas tardes, bienvenidos a otro seminario de máster. Hoy tenemos con nosotros a Lübekke de Geomar. Lübekke es oceanógrafa física y trabaja en Geomar, en Kiel, en Alemania, en cuestiones relacionadas con variabilidad climática tropical. Obtuvo su doctorado en la Universidad de Kiel en 2010 y pasó casi 3 años como postdoc en Seattle, en Estados Unidos, en el CMI. Antes de regresar aquí como profesora junior en 2014. Ahora mismo es ya científica senior en el Geomar y su investigación se centra en la variabilidad interanual y decadal de los océanos en la atmósfera, sobre todo relacionadas con los niños del Atlántico y en Miguel. Bueno, hoy os hablar de los cambios recientes en la variabilidad atlántica tropical.
Yeah, thanks for the introduction. I understood some pieces of it, so Okay, yeah, so I want to report a little bit on what we did about recent changes that we found in tropical Atlantic variability. And I should say that a lot of the results I'm going to show are actually the ones of my former PhD student, Arthur Pigeon, who's now postdoc in TS. And there's also a lot of input from other people from the group of physical oceanography at GEMA, Rodrigue and Peter Brandt, and also Mujib Latif from the climate modeling. Okay, so just to orient ourselves, where are we? I'm going to talk mostly about this region here, so the tropical Atlantic region, where we have the northeasterly and the southeasterly trade winds that push the warm water to the western side of the this is sea surface temperature here and wind stress in this figure. And so we see the warmer temperatures here on the western side, where we have the warm pools, and then cooler temperatures here in the eastern side, which we call the cold tongue region. And when we look schematically, kind of like as a slice here through the basin, with the western tropical Atlantic here and the eastern tropical Atlantic here, we see this pool of warm surface water that's here in the west. This also leads to a tilting of the thermoclines of the boundary between the cooler waters below and the warm surface waters. And as I said, this is done mostly by the wind stress that is pushing the waters here to the west. And also we have convergence, atmospheric convergence over the warm pool, so rising air, and then we have subsidence over the cold tongue. Okay, so these are things to keep in mind for the variability that I'm going to talk about. So the variability in this region is actually mostly governed by the seasonal cycle, or that's the dominant signal if you just look at how temperature is changing. And shown here is kind of a Hochweiler diagram, so it shows time on the y-axis from January to December, so that's a climatological average over many years. And we go across the basin here from the western side to the eastern side in this panel, and then further down here the coast of southwestern Africa in this panel. And we can see that we have the warmest temperatures here in boreal spring, so around March, April, May. This is when the intertropical convergence zone is closest to the equator and relatively weak winds on the equator. And then towards the boreal summer, the winds are picking up, the ITZ is moving northward, and we have more upwelling and this formation of this cold tongue here in the eastern part of the basin. When we look here along the coast, we can see that there's a pretty strong boundary, a very huge gradient here at around 15 to 17 degrees south. That's the so-called Angola-Benguela front, and this is where the warm tropical waters that come here with the Angola current from the equator meet the cooler waters that come from the south with the Benguela current. And we can see that there's also some seasonal modulation, so the front is furthest to the north here in the boreal zone. Okay, so if we look at an area average here over the cold tongue region, which is also called the Atlantic 3 region, so that's from 20 degrees west to 0 east and from 3 south to 3 north, and this shows a time series here. We can see again the seasonality, right? There's always warmer temperatures in spring and cooler temperatures in summer. But we can also see that there is some modulation of that. It's not the same every year. And so if we take this seasonal cycle calculated from this longer time series and subtract the repeated seasonal cycle from this time series, we end up with what we call these interannual anomalies, so the deviation from the seasonal cycle, so to say. And we can see, so the scale is chosen for comparison with ENSO, so it's a little large here, but we can see that they reach about 1 degree or something of these anomalies. And this is actually the variability that I'm going to focus on, so this interannual variability. Okay, when we look at that more in the map view, so this is now the standard deviation of these interannual sea surface temperature anomalies from an observational product. And shown for the whole tropical Atlantic, we can see that there are some hotspots of this variability. So one is the cold tongue region that I just showed as an example, but also here down the coast of southwestern Africa, what we call the Benguela area, or off the coast of Angola and Namibia, we have very strong variability, and also here in the northern upwelling and northeastern tropical Atlantic upwelling system. And I want to focus on these two areas here. So for one, this Atlantic 3 region that I just introduced, and the other one is the so-called Angola-Benguela area. And for both of them, we see a time series of these interannual anomalies. And these dotted lines here mark one standard deviation. And we can see that there are these events where the temperature is warmer than the standard deviation for several months, or cooler than -1 standard deviation for several months. And these events are what we call the Atlantic Niños, if they happen here in the cold tongue region, or the Benguela Niños, if they happen here in this region. So this is analogous to El Niño in the Pacific Ocean. The name comes from El Niño in the Pacific Ocean. Okay, so why do we care about these events? Well, they have some implications, for example, for rainfall. Shown here is the first EUF of rainfall variability in boreal summer. Or I should say that, before I go to that, I should say that these events, these Atlantic Niño events, they tend to peak in boreal summer. So they are strongest in June, July, August. And these Benguela Niño events, they often happen in March, April, May, so a little bit before that. And sometimes they are connected, so often these events happen together in the same year, but not always. Okay, so for the boreal summer months, we see here the first EUF of rainfall variability, and that's the gray shading, and then the color shading is the sea surface temperature pattern that is associated with that, so the first principal component regressed into the SST field. And we can see that this resembles pretty much these patterns of where we find the highest sea surface temperature variability. And indeed, when we have some such warm events, this relates to rainfall variability both over Africa but also over Brazil. And in this study here, they looked specifically at correlations between the sea surface temperature anomalies in this Benguela region and over this region here a few months later. It's also related to anomalies in the marine ecosystem here along the coast. So you can imagine if it's much warmer, then some of the biological activities, some species might like that, others not so much. For example, bigger fish don't like it if the temperatures get too high, so they are migrating, so then this has impact also on fisheries and the economy there. So these are just two cartoons from a meeting a few years back where there was someone drawing these cartoons. So this is about the precipitation effect, and this is about the fisheries effect, where the fish here see the forecast that it's going to be warm again, and they say, oh, let's go south then, let's go away from that. Okay, so that's what we care about. We want to understand what drives these events and whether this might change into the future with the changing mean state with global warming. So for these Atlantic Niño events, there are a number of different mechanisms that have been described to contribute to the generation of these events. So they are, as we have seen in this time series, they are not as big as ENSO events in the Pacific, right, where we have very clear signals that one can investigate. So here, even some rather small fluctuations in temperature can give rise or can already count as an event, and so they are, depending on when they happen, there are different mechanisms that can contribute, but most of them, and we try to summarize them here in the review paper a few years back, but the main mechanism, I would say, that is behind most of these events is the Bjerknes feedback, which is also causing ENSO or is governing ENSO in the tropical Pacific. So and that's a positive feedback loop between sea surface temperatures here in the eastern equatorial basin, wind stress to the west of it, and the thermocline depths along the basin. So in a way that if we have a warm anomaly here in the cold term region, you can imagine that this temperature gradient that I showed in the beginning between the cold term and the warm pool, that's weaker than normal, and that also weakens the surface winds. And if we have weaker winds, that leads to a relaxation of the thermocline slope, and so we get more warm water again in the western, in the deeper eastern basin, and so then again there's warmer water that is upwelled and mixed to the surface, so it amplifies the warming that we had in the beginning, and it works the same for cold anomalies. So that's true for most of the events, but actually not all of them. So sometimes we find warm events and there are stronger winds. And there are also a number of mechanisms that have been suggested that could explain that. And two of them, so this Rossby wave reflection and meridional advection, have to do with a wind stress pattern that leads to wind stress curl anomalies to the north of the equator, and these wind stress curl anomalies lead to a deepening of the thermocline. There are subsurface temperature anomaly that's shown here. And the subsurface temperature anomaly can then either be communicated via Rossby waves to the western boundary and they're reflected into a Kelvin wave, that's one mechanism, or it could also maybe be advected towards the equator by the climatological currents. And then there are also these deeper in the basin, these deep jets, so they are alternating westward and eastward jets, and you can see here schematically that they have a downward phase propagation, which means that they have an upward energy propagation. And it has been suggested that maybe that could also impact SST, although it's not really clear how it gets through the strong equatorial, how the signal gets through the strong equatorial undercurrent. And then last but not least, heat fluxes, so short-wave radiation and maybe also reflected outgoing long-wave radiation have been suggested to contribute to a warming, although mostly I would say heat fluxes act as a damping of these anomalies. Okay, for the Benguela region here, there are maybe two kind of like competing mechanisms that have been described. One is pretty much similar to the forcing or the Björken's feedback forcing, so also there we get wind anomalies here in the western part of the basin, and that they drive this relaxation of the thermocline via the propagation of downwelling Kelvin waves. Here that's schematically illustrated here. So they propagate to the east, and then part of their energy is transmitted poleward as coastally trapped waves. And so they can impact the depth of the thermocline here along the coast, and by that again then warmer waters or cooler waters are upwelled or mixed to the surface. And you can see at this list of studies here that I think for most of the time and until a few years ago, I think most people would have agreed that that's the dominant forcing mechanism for these Benguela media events. But there have been a few studies, and I will come to that later in the talk. More recently, it seems that also these local wind events directly at the coast can also have a strong impact. And I mean, we are in a weak upwelling regime, so typically the winds are towards the equator, so you can imagine that if the winds are weaker, the upwelling is weaker, there's warmer water. But the upwelling is not super strong to begin with in this region. Most of the upwelling region is actually further south. But still, so that could play a role. Also here, heat fluxes and this advection of warm water from the equator, if there's more or weaker advection of this warm water. And also I will say a little bit about the role of freshwater fluxes later, showing an example. Okay, so coming back to this plot here, where we see the time series of the interannual sea surface temperature anomalies averaged over these two boxes, we can kind of draw a line around the year 2000 and see that most of the big events here happened before that, right? They happened in the 80s and 90s. There have been a number of these bigger Atlantic and Benguela Nino events, and since 2000, really not so much. So the variability was much more muted after 2002 until maybe 2017 or 18. And so this is something that Arthur has addressed in his PhD work. And so he has quantified first this visual impression that the variability might be weaker. And so we see here the difference in the standard deviation between this period after 2000, this is shown in blue here, and the 80s and 90s, which is shown in red here. And so everywhere where it's blue, the variability has been weaker in the second time period. And we can see this pretty much for all of this region where we have this high interannual sea surface temperature variability, the variability weakened from one period to next. Oops, okay, so something went wrong here. Looks like the plot has been, I don't really know what happened. Okay, but what this was to show was this is mainly a summer effect. So maybe you can kind of, okay, so this is, for some reason it's showing twice the same thing, but only half of it. But, well, really punched together. So it shows again a Hoffmann diagram from January to December, and then across the basin, and it shows the standard deviation of the sea surface temperature for the first and the second time period. And so what you maybe can see is that it really peaks in boreal summer, typically, or in the 80s and 90s there was this really strong peak in boreal summer, and then in the second time period this got much weaker. And there's also a little bit of a second peak here around November, December, and this didn't really change much from one period to the other. Okay, so we were trying to understand why the variability was weaker in the second time period than in the first one, and since we know that the Bjerknes feedback is behind most of these events, we looked at changes in the components of the Bjerknes feedback. So we looked at these three components: the wind response to a sea surface temperature anomaly, a thermocline depth response to a wind anomaly, and the coupling between the depths of the thermocline and the sea surface temperature anomaly. And these are the three components here. And always the red line shows the first time period, and the blue line shows the second time period, and all these thin line here shows different reanalysis products that we looked at, so to see if we find a consistent change between different products, and the thick line shows the average. And so we can see that in general this wind response to, or this relationship between wind and sea surface temperature is strongest more towards boreal spring, and there it didn't change that much, but when we look here at the summer months, there's a little bit of a decrease towards the second time period. I think this is clearer here in the second part of the feedback. So if there is a wind, anomaly, the thermocline is not reacting as strongly to it. And also the subsurface-surface coupling is reduced here, especially for the summer months. And I'm not showing this here, but there's also a stronger heat flux damping in the second time period. So for the same sea surface temperature anomaly, the damping by the latent heat flux is stronger. Okay, we try to understand why this might be the case, why there might be this change, and we try, again, same problem here with this figure, try to relate that to what the winds are doing. So this is the similar picture as before for the sea surface temperature, so for all the calendar months and along the basin. But it shows the variability in the zonal wind. And we can see that typically the zonal wind variability is strongest in the boreal spring, and it got much weaker in the second time period. And we believe that this might have something to do with the fact that the Walker circulation, so the atmospheric circulation style with the rising branch over the warm pool and the subsidence over the cold tongue, shifted a little bit towards the west, because with global warming we have more, the land is warming faster than the ocean, so we have this stronger contrast, and the Walker circulation is shifting a little more over land. And so if we have wind variability over land, the ocean will not see it, right? So that's the idea behind that. Okay, so what about this other box here, the Benguela region? And there we also see a really strong reduction in the variability in the after 2000 compared to the 80s and 90s, and we can also see this here as a function of calendar months. So the red line shows the first time period, the blue line the second time period, and in general the variability is strongest in boreal spring, and that's also where we have a strong decrease. Okay, so we know that there are these two kind of competing mechanisms about the remote forcing and the local forcing, but both of them are related to the wind stress. And so here we looked at the relation between the sea surface temperature anomalies here in this box And the wind stress in the whole tropical Atlantic Ocean, so it's a regression between sea surface temperature anomalies here onto the wind field, with the winds leading by 1 month. And for the first and the second time period. And it's maybe a little hard to see, but here in the first time period, we see that there are really strong wind stress anomalies here in the western equatorial Atlantic, so a weakening of the trade winds that are typically southeasterly here. Which fits perfectly to this remote forcing mechanism, right? So that you have a weakening of the winds here, and that generates a Kelvin wave that propagates across the basin and then down the coast. In the second, there's not much going on here in the box itself, so that the local winds didn't really play a role for these events. And when we think of the biggest Venezuela Nini events that happened in the 80s and 90s, there was one in 84 and one in 95, for example. They have been very well documented to be that they were generated by this remote forcing mechanism. So for the second time period, there is still some wind anomaly here on the equator, but it's weaker, especially here in the far western part, and there seems to be more connection to the local winds there. So this would suggest that maybe the relative role of the local forcing increased in the second time period. And this is also highlighted by the second plot here, where we looked at the relation between the thermocline depth and sea surface temperature. So this is now a regression of sea surface temperatures everywhere onto thermocline depth anomalies, taken here as the depth of the 20°C isotherm in this box here in the Atlantic Sweep region. And we can see that in the first time period, of course, there's a very strong relation in the box itself, right? So the sea surface temperatures react to the thermocline depth right in the box. But also here for this region, right? That's a really strong relation. And for the second time period, really not so much, so it's much weaker. Okay, and so we believe that probably in the second time period, this remote forcing mechanism for some reason didn't really act as strongly, maybe because the wind variability has weakened anyway, so there were not that strong Kelvin wave anomalies that propagated. And I want to show one example of one of these locally forced events that happened in the second time period. And that's the Venezuela Nino of 2016 that we can see here. So this is obviously a global map of sea surface temperature anomalies, and what jumps out at you is the El Nino of 2015-16. But we can see that there was also the strong warming here off the coast of Angola and Namibia. And this is for the end of January of 2016. So if we zoom in a little bit here, this is now from NOAA, the sea surface temperature anomalies averaged from mid-January to mid-February, and this is just here at the coast. We can see relatively widespread warming, and if we average again over this box, so from 10 south to 20,000, from 8 east to the coast, look at the time series here, we see these Venezuela Nino events that I just talked about of 84 and 95, there was also one in 2011, and then there's this one of 2016. And I put them all on top of each other here so that we can compare them easier. And we can see that it was maybe not quite as strong as the ones here in 84 and 95, but still the peak anomalies here were above 3 degrees. And also what's striking is that it happened very early, right? I just showed you that the main peak of these events is in March, April, May, and this was for all of these other events, this was true. But this 2016 event happened already in January, February, and it was very short, so it just was over after a few weeks. Okay, so we tried to understand what generated this event, and these were our suspects that we have looked at. So since we knew that most of the events are forced by Kelvin wave forcing from the equator, that was the first thing that we looked at, and then also at some more local forcing mechanisms. Okay, so to find out whether there was Kelvin wave forcing for this event, we looked at thermocline depth anomalies and sea level anomalies across the equator, and then for sea level we can also do that along the coast. So the left one here shows Z20, so the depth of the 20°C isotherm anomalies from the Pirata moorings. So we have there are moorings here along the equator. And they have been in place since about 2010. We have good data, and so this shows time running from top to bottom now, and the longitudes here along the equator. And you can see that, for example, for this 2011 event that I just showed, there's a structure that you can see that's propagating across the equator. Right? If it's red, then it's corresponding to a deepening of the subicline, so downward in calibrate. And we can also see that in sea level, and we can see that so after this bar here, it shows the track here along the coast, with its latitude then down to 15 south. And we can see that the signal in 2011 is continued along the coast, so depending on the thermocline. So, but for 2016, there's really not that much to see, right? At best, there's a very weak anomaly here in Z20, and it's very hard to see anything in sea level here. There's a deepening of the thermocline right at the coast, but it's not really connected to what happens at the equator. So we were really surprised and looked at it and said, okay, so obviously this was not really a remotely forced event, so how was it forced? What happened? And so we looked at the winds to see if maybe the local upwelling could have played a role. So this is wind stress anomalies now from satellite winds, and just to remind you again, typically we have southerly winds, so we are in the southeasterly trade wind regime. So if the winds are northerly, that means that we have a weakening of the winds. And maybe a little hard to see, but there is, for most of these months, north of the front, north of 15 south, there is a weakening of the winds during that time. And during January, this also continues south of the front. So just from that, we could conclude that maybe there was less upwelling, and this reduced upwelling could have played a role. So upwelling is really something that's kind of like hard to judge, right? You don't really have measurements of vertical velocities and so on. So one other thing we looked at was the cross-shore velocities from the Oscar product. So in an upwelling region, if we have water coming up from below, it has to go somewhere, so it's going away from the coast because it can't go into the land. So you typically have a velocity at the surface that's directed away from the coast. And so we looked at anomalies in this cross-shore velocity, and I want you to focus only on the red line here. We see that during this event we had relatively high anomaly in this cross-shore flow that was towards the coast, so east, towards the east. So this means it's a weakening of this away from the coast transport. So this again suggests that maybe upwelling was weaker, and this could have played a role for this event. Okay, if we have weaker winds, we might also have less latent heat flux from the ocean to the atmosphere. And we looked at the heat fluxes, and wherever it's red, the ocean is losing less heat to the atmosphere than typical. And the upper panels here show the latent heat flux, and the lower panels show the net surface heat flux. And first you will recognize that they are very similar, so the net surface heat flux is really dominated by the latent heat flux anomalies. And so in the anomaly center, otherwise of course short wave anomalies. And this is again for the months from November to February, so the event peaked in January, or towards the end of January. And we can see that here to the north of the front, where we have these weaker winds, the ocean is also losing less heat to the atmosphere. But as soon as there's a warming at the front, the heat fluxes are damping again. So we think that maybe it contributed to the warming to the north of the front that could then be advected towards the front, but directly at the front, the heat flux is acting as damping. Okay, so was there advection of warm surface water, more advection of warm surface waters towards the front than usual? And for that, we looked at velocity data from a mooring that we have at 11 degrees south, so somewhere here. So this shows the zoom of this. And right here off the shelf, there's a moored upward-looking ADCP. And we have mooring data there since August of 2013. And this is not anomalies, this is actually total velocities. So the first thing you will notice is there's really no continuous Angola current that's always southward and bringing warm waters from the equator to this region, but it's actually very variable. But during the time of the event, they were actually northward velocities, we call it, from the marine. But we don't have, because it's an upward-looking ADC period, they're scattering towards the surface, we can't really use the upper 45 meters or so, we can't say anything about that. So for the surface velocities, we use geostrophic velocities from the Oscar product. And we can see here that for most of the time period, they align very well, right? They fit really well. But during this event, they were strongly southward, while the velocities further down were strongly northward. And so this suggests two things. The first thing is there must have been high stratification because it was really baroclinic, right? So the surface did something completely different than the subsurface. And also, if there was warm surface water, maybe because of the heat fluxes, then they could have been advected towards the region. And this would also kind of like explain why the event ended so abruptly, right? If there's only just like a very shallow amount of warm surface water and it's not really going deep towards the subsurface anomaly. So I showed you this plot before, now I wanted to focus on the black line. The black line is now showing the anomaly in the alongshore component. And we can see that really during this event there is a really strong anomaly in the southward anomaly of the alongshore component of these Oscar velocities. So again, this would suggest that if there's warm surface waters towards the north of the front, they are really advected to the front with this surface current. Okay, so then of course we wanted to know why was there such high stratification, right? Why is the flow so baroclinic during this event? And for that we looked at salinity. And so this is salinity from a satellite product here from the ESMOS. And this shows now, so this is total salinity, not anomalies, shown from 2010 to 2017 along the coast, so from the equator down to 25 south. And you can see that there are low salinities pretty much every year in the beginning of the year, right? And most of it is, I think, is due to the Congo River discharge, or at least the part that's south of 5 south. There's a lot of discharge during that time. But in 2016, and precipitation. But in 2016, it's really the salinity is lower and it's reaching further south than during typical years. And we can see this in an anomaly plot here. So this is sea surface salinity anomaly in February 2016, and we see this really blue blob here. So it's really a lot fresher than usual. But we can also see that it's saltier towards the west than usual. And so what we think is that typically the Congo River outflow here at about 5 south, it typically goes into the ocean, typically takes a westward route. And it's not really clinging to the coast. But sometimes if the wind is such that it kind of like deflects towards the south, and then you have more fresh water here in the coastal area. And this is what seems to be what probably happened in 2016. And also when we look at precipitation, so this is now during the event, so in February 2016, we see that in the area itself there was higher precipitation, so this shows the time series here, or the anomalies of the small box, and then zoomed in here just for 2015-16. You can see that this was one of the highest precipitation anomalies that happened during this time series, right over the ocean. But also if we look a few months before that, so in November 2015, we see that over the catchment area of the river, so where all of the Congo River gets its water, there was a lot of anomalously high precipitation there overland. So this would also suggest that probably there was enhanced river runoff during that year, and also that it took this north-south route. Okay, so if we have this freshwater, kind of like freshwater lens on top of the ocean, we can create something that's called a barrier layer. And a barrier layer means that the mixed layer measured in terms of density is really determined by the salinity. And we can see this here, so there was an Argo float in the area right here in 8 south, 12 east, so somewhere here where we have the strong freshwater anomaly. And we see here the upper 100 meters of the Argo profile, and the red line shows salinity, the green line shows density, and the black line shows temperature. And so of course, I mean, we are in an area, we are in an upwelling area, everything is very shallow to begin with. But still we can see that we have super low salinity values here, right over the upper 5 meters, right? It's at about 30 PSU or something. And then it increases to 35 point something within only a few meters. So there's really a super strong salinity stratification. And this really sets the density. So if you determine the mixed layer depth by a density criterion, you will get this super shallow 7 meter or so mixed layer depth. But the isothermal layer, this is actually deeper. And if you have a situation like that, then you can imagine the cold water that wants to get to the surface with the upwelling and mixing, that's really sitting here, and this layer here kind of like acts as a barrier to the communication of this colder water. So it's not really clear how much, it's very hard to quantify how much this really matters, and this is something that my PhD student, Leo, is currently looking at to try to quantify this effect of if we have a strong salinity stratification, how much this can actually inhibit the upward movement of the cold water. Okay, so to summarize, for this 2016 Benguela Nino, we found that it was not predominantly forced by an equatorial Kelvin wave, but rather by a combination of local effects. So we had weaker longshore winds and enhanced freshwater input. And so the weakened winds led to reduced latent heat loss from the ocean to the atmosphere. The freshwater input from the river and precipitation led to this enhanced stratification. So we have this very shallow layer that can then be advected southward by the surface currents, and also probably led to less diapropyl mixing, and maybe there was also less upwelling because of this. Okay, and to conclude in total, so we have seen that the sea surface temperature variability in the southeastern tropical Atlantic decreased after 2000, or I should say in 2000 to 2017, because that's the period the study was focused on. Since then, we have seen 2 big events in 2019 and 2021. So we'll see if the trend continues, if we go back to a state of higher variability, or if this is just one hiccup and then we go further into weaker variability. And for the equatorial Atlantic, it seems to be related to this weakened Bjerknes feedback and maybe to the Walker circulation shift towards the west. And for the Benguela Niños, we think that there have been less impact of this remote forcing. And I showed you this example of an event that was mostly locally forced. Okay, thank you.
Thank you very much. Okay, I have a question because you say that 2016 is an example of a mostly locally forced event. But when you saw the estima global, there is an Niño.
Yeah.
And I think that maybe this rainfall over the region of Congo River could be.
I get this question a lot because I always show this. I always start out with this plot, right? So everybody thinks, oh, there was an El Niño. It must have something to do with it. I never get around to checking that.
And it was looking at El Niño.
Yeah.
And also there is an upwelling in the North tropical region of.
Yeah.
Yeah. Which could be in agreement with 2 waves.
I mean, for the northern tropical Atlantic, I mean, this makes sense, right? We know that there's the connection to the winds. For the south, I mean, there's this one paper now, I think, by Mathieu and Serge, right? Kind of like trying to align that.
Maybe not by the winds, but by rain.
Yeah.
I mean, altering the sea level pressure and then the
I think there is a relatively robust connection between ENSO and the shift in the South Atlantic high. But yeah, I think it's not really consistently typically related to what happens in Benguela, but I should check that again for this event.
So it's a possibility.
Yeah, definitely.
Rainfall.
Yeah.
And so when you talk about local effects, you mean that the stratification will.
Well, I mean, in contrast to a Kelvin wave forcing from the equator, right? I mean, with regard to Benguela Niños, this is kind of like what we call a remote forcing if it's forced by winds in the western equatorial Atlantic, and in contrast to that. But of course, I mean, the things that the wind weakening and stuff like that, it's not, it doesn't have to be stochastically local wind variability. It can be influenced by whatever, El Niño or something. Yeah, that's a good point. Yeah.
I have a question about if you have any hypothesis about why in the last period the remote forcing from the waves is not working at all. I mean, do you think that maybe the stratification along the equator has changed and is less receptive to trigger waves that can propagate them along the coast? Or because in the Hofmühle you show, I think there are some events that can reach Benguela.
Yeah.
But why do you think you don't have this remote forcing?
I'm not sure. I mean, one aspect is that, but I'm not sure if we have, and we probably have, but I can't remember, compared the standard deviation in SSH or thermocline depths, if it's going down as well. I'm not quite sure. I think one aspect is that there has been less wind variability in the western equatorial Atlantic, so that would automatically lead to less Kelvin wave forcing. But Arthur has tried really hard to relate that to mean state changes in the equatorial Atlantic, and then, I mean, the thermocline has hardly changed, even SST. I mean, there's this warming hole that Hyacinth published about during that period, so the mean state change is really not that dramatic in the equatorial Atlantic during that time. So it's very hard to relate that.
But I remember something that we have like a flattened thermocline.
That's really depending on the time period that you are looking at.
I don't remember. Because also the pattern that you said that the wind, you reduce the variability in the wind in the west, but it's like shift to the east, the impact of also the anticyclone. If you put the figure, the winds, yeah, this one, I think it's the other one. The previous one, yeah, this one.
Okay. Yeah.
You have like a displacement to the east, right? So you have.
You mean here from the whole anticyclone?
So maybe I don't know.
Yeah. Yeah. I'm not sure either. I mean, it's
Okay. Thank you.
I mean, it's also it's statistic of rather small numbers, right? It's not that many years. So we have to also look at long model simulations, PI control simulations, and pick like 30-year periods and try to relate the standard deviation of the SST to something in the background state, and it's really, yeah, the internal variability is huge, so it's not really clear.
Another question. When you talk about the plume of the Congo River,
yeah,
you said that the winds deviate the plume.
I'm not sure. So there's this study by Michael Sena Martens and Detlef Stammer. They have looked at the salinity. I think they've looked at salinity variability and related that to the Congo outflow. And they've seen that mainly this plume is mainly going in this direction, and so they conclude that typically it shouldn't impact sea surface temperature variability here at the coast because it's just not really reaching the coast. But then they said there are years in which they see the more fresh water actually taking this route, and I think this just, I mean, I haven't really confirmed, but it looks like it, right? Because there's this higher salinity here and this lower salinity here. So it looks like typically it's going here, but in this year it's going more here. But I'm not quite sure what the wind condition really is that needs to happen for that.
Okay, so well, if there is no more questions, well, we can close the talk. Okay, thank you very much for your participation.
Yeah, thanks for having me.